Mm.
Professor Chen, could you make a full screen of your slide?
Yeah, let me do this.
Okay. Yeah.
Yes.
Okay. Okay, then, yeah. Let's start our space seminar. Good morning, everyone. We are pleased to have Professor Kang Chen for today's speaker. Let me introduce him briefly. Professor Kang Chen received his PhD from UC Santa Barbara in 2010. He was a postdoctoral fellow in University of Colorado Boulder and University of Toronto during 2010 to 2015. He then joined Fudan University as a faculty member during 2015 to 2018. Since 2018, he has been with the University of Hong Kong, where he is currently a professor. Professor Chen has been working on strongly correlation theory. His research focuses on the quantum magnetism, quantum spin-ice, and strong spin-orbit coupled material, as well as ultra-cold atom optical lattice. Today, he will give a talk about surface magnetism and fractionalization. Please welcome Professor Chen.
Thank you very much for the very nice introduction. Also, thank you for inviting me to this seminar during this very difficult time. Yeah. So thanks people for attending this seminar. So this is about surface magnetism and fractionalization on a surface. So so the outline is as follows. So I will first talk about the first part of the seminar about the interplay between surface magnetism and Dirac fermion in so-called magnetic topology insulator. So after this, I will talk about the surface fractionalization and the time reversal anomaly on the surface of a cluster model insulator. It's called 1T titanium disulfide. So let me begin with the first part, which is interplay between surface magnetism and the Dirac fermion in magnetic topology insulator. Let me just give a brief introduction about magnetic topology insulator or topology insulator. So this is a work with my graduate student, Shiping Yao, who was my graduate student at Fudan. I brought him to Hong Kong with me, and this is my Chao Kai Li is my current postdoc. So they contribute heavily to this work. So this is the introduction of the first part. So in last a decade or so, maybe even more than a decade, we have seen a great development in the field of topological band structure. I think almost 1.5 decades since Charlie King and others proposed the idea of quantum spin Hall effect and the topology insulator. So this is the sorry, I have an interruption here. So yeah, so this is the band structure of a band insulator, and the left one is a trivial band insulator. The right one is a topology insulator. So there is so this gamma A and gamma B are so-called time reversal invariant momenta, and then it has to be a Kramers degeneracy here. And the way these Kramers degenerate states are connected, there are two different ways of connecting them. This is a so-called trivial way. This is this non-trivial zigzag fashion. So in this non-trivial way, if you put regardless of where you put the formula, there is always a so-called cosine, and this cosine is a surface state. So Charlie Kane and others, they noticed this this distinction between a conventional trivial band insulator with this topological insulator, and proposed this concept of so-called Z2 invariance for two-dimensional topological insulator, and then generalized to 3D. And this is an example of this edge states, that the boundary between a conventional trivial band insulator and quantum spin Hall insulator. Nowadays, it's called Z2 topological insulator. And in this part, it assumes there is a global U1 spin rotation symmetry where spin quantum number either spin up or spin down. But in reality, it doesn't really require global U1 symmetry to have a quantized, to have a conserved SZ quantum number. So really, because of spin orbit coupling, so we do not have a global spin rotation symmetry, and they have this time reversal related protected edge states. So this is a so-called two-dimensional topological insulator, and later on, was generalized into 3D, and so this is a distinction between so-called many will focus on this one, where then there is always this kind of crossing. If you go from time reversal invariant momenta to other time reversal invariant momenta, there is always crossing at the Fermi level. So this crossing from a Dirac so-called Dirac electrons, and they touch at the gamma point. So this is a strong topological insulator in 3 dimension. So since then, many of these topological insulator, in general topological insulator and semiconductor are classified, and this is so-called tenfold way. Given the time reversal symmetry and particle symmetry and the combination of them, so one can figure out the table, a periodic table, so-called tenfold way, to classify all possible topological phases, topological insulator and topological semiconductor in various dimensions from 1D to 8 dimension, but we're only interested in up to 3 dimension. So this is the theoretical development, and later on, people are interested in going beyond the simple band insulator. Can we understand the semi-metal? And so this is the only proposal of topological semi-metal, or so-called Y semi-metal, where there is a Y points in the bulk spectrum of the 3-dimensional material. And many progress has been done. Many works has been done. So the focus of this talk is not about semi-metal; it's about magnetic topological insulator. So magnetic topological insulator was initiated, almost initiated, I think it's maybe 10 some years ago, after the discovery of topological insulator in 3-dimensional topological insulator in bismuth selenium. So later on, theoretical physicists like Shu Chen Zhang were thinking, if we introduce magnetism into topological insulator, can we try to gap out the surface Dirac electron and convert the Dirac electron into something called a quantum anomalous Hall effect? And this is the original idea by Duncan Haldane in the 1988. So this experimentally was realized by Qi-Kun Xue's group in Tsinghua. So his group successfully grew many samples with bismuth selenium doped with transition metal ions such as chromium, such as other transition metal ions, which introduce magnetism on the bismuth selenium surface. So it turns out, because of the single ion allotropy on this chromium local moment, so the magnetic moment of the chromium ion actually form ferromagnetism. And it's really because of this is a 111 surface. There is a strong single ion allotropy on the chromium ion. So the magnetic moment of chromium moment is pinned to this 111 direction, which is normal to the surface. So when the ferromagnetism appears in this sample, so originally there is a surface Dirac cone, and there is time reversal symmetry protected by due to the 3-dimensional topological insulator. So when time reversal symmetry is broken, so the protection, time reversal symmetry protection of the Dirac band touching is gone. So then you will generate a mass gap for the surface Dirac electron, and turns out this is a Chen insulator. So the field valence band has a non-trivial Chen number, and the Chen number equal to 1. And because of this presence of finite non-zero Chen number, there would be a edge state going around the boundary of this thin film. And if you measure Hall resistivity, Hall conductance, it should be quantized up to E squared over H. And experimentally, they do observe sequence phase group at a greater advance in making these very nice, beautiful samples, and they carry out a very low temperature Hall resistivity measurement, and they do find a quantization at 1.5 Kelvin. So the summary of this slide is so if you have a Dirac fermion, whatever here is due to the surface protection, a time reverse symmetry protection of the on the surface of a three-dimensional topological insulator. And if you introduce ferromagnetism, so it's the interplay between itinerant electrons. So itinerant electron is a Dirac fermion, and then you introduce a local moment. Introduce this skyrmion magnetic ion. So the skyrmion introduces ferromagnetism. So if you put the Dirac fermion together with a local moment of ferromagnetism, so this local moment of ferromagnetism will modify the band structure topology of the Dirac fermion, in this context, Dirac fermion. So they will convert it into something non-trivial, which goes Chen insulator, and they give you a robust quantized Hall conductance. So,
can I ask the question?
Sure.
So
Yeah, feel free to interrupt, by the way. Yeah.
You mentioned that here the single ion is important, right? To see the magnetism. Is it correct?
Yeah, I think so the way to understand is so this is a 1-on-1 surface. So this is 1-on-1 surface. So it has a 3-fold rotational symmetry. C3 rotational symmetry. So if you introduce chromium, so this C3 rotational symmetry requires the presence of this single anisotropy in this 1-on-1 direction or SZ direction. So and because this chromium is a spin 3/2, so it's not a spin 1/2. So it's a spin 3/2. So this single anisotropy is necessarily there, allowed by symmetry, and because of that, it pins the magnetization, a magnetic moment to this Z direction, which is not same.
Yeah, but the question here, the magnetic ion is does not form a periodic structure, right? It's kind of a form of the magnetic impurity that's spread it over the sample, right?
Say it again. I didn't hear very well. So
here the magnetic ion does not form the periodic structure. It's just introduced to the system as a kind of magnetic impurity, randomly actually distributed over the surface, right?
Yeah, so that's right. It's not a periodic. It's more like impurity, and it's replacing. But it's on the C3 rotational axis. It is on the. So if you sure, you are saying because of this disorder, or because of the randomness, the global symmetry of the lattices may not be exactly before.
Right.
Sure. I agree with that. But yeah, I agree with that. Yeah, there could be other magnetic states. Yeah.
Also, the origin of the magnetic interaction is also, I remember, quite controversial in this system. So I don't know how important is the single ion anisotropy, I think.
Yeah, so I agree with that. So if one integrate out the Dirac electron, you generate various RKKY interaction, and because of the Dirac fermion, because of the valence density of states at Dirac point, so the RKKY interaction can be of some special form. Yeah, I agree with that. But so one can because this is experimental observation. So we can just rely on the experimental observation here. Right?
Okay. Discuss for the later. Thank you.
So Yeah. So the short summary is this is a example of interplay between conducting electron and the local moments. And when you put both of them are rather simple. You know, ferromagnetism is the oldest and the simplest magnetic state. And Dirac fermion is due to time reversal protection of the three-dimensional topological insulator, and it's also very well understood. But if you put these two simple objects together, it will generate something. You know, this will generate something very very interesting. It's a two-dimensional chain insulator here. Okay. So the question we are going to address is so we want to understand the impact of various magnetic texture beyond the simple ferromagnetism. In this context, we want to modify this part. We want to ask if we have other magnetic states, and then we place this magnetic state on top of the Dirac fermion. What can happen on the right hand side, right? Yeah, so this is a very simple piece of work, and so this is a context. This is also belong to the context of where so-called the real space topology meets with the momentum space topology. What will happen? So so we modify this part. We introduce a real space topology in the magnetic sector, and the Dirac fermion has well, in this context, carry some features of momentum space topology. And then we put this real space topology together with this momentum space topology, and want to cook up something interesting on the right hand side. Yeah, so and this is some plot of this is a typhoon, which is the real space topology, and this is so-called magnetic skyrmion. It's a real space topology in the magnetic sector. So let me see the time. Okay, I think I'm doing well with the time. Let me just give a very small, several simple example of the meeting between real space and the momentum space topologies. It's a very personal summary, and so this is a list of them. I made a list summary of this. This is some. So one example is this mini gap modular fermion in vortex lines in three-dimensional semiconductor, regardless whether the semiconductor is topological or not topological. So vortex line can hold the mini gap modular fermion. So the other is skyrmion, which is a topological real space topological object, can carry charge, and if it is condensed, can induce activity. So Kaya domain was of topological surface, and so-called also like bilateral graphene. So if you apply magnetic electric field, like sometimes you can have this chiral mode. And this is also real space topology. Let me just give this simple example. And this was developed by Ashwin about 10 years ago. And at that time, there is an experiment where if one dope copper, if you introduce copper into bismuth selenium into this three-dimensional topological insulator, and the system becomes semiconductor. And Ashwin proposed this idea: if we consider a three-dimensional semiconductor, and if we apply field, it will generate vortices. And he is treating this vortices is a real space topological object in semiconductor. So if you treat this vortex as a one-dimensional object, and you can study the band structure or this electron property along this one-dimensional object. And it turns out that when the presence of the absence of this anomalous mode of this one-dimensional vortex line is related to there is a quantum number, there is a Z2 quantum number of this one-dimensional object. You can when this Z2 number is non-trivial, you will have this anomalous mode. If it is trivial, you will have the Majorana anomalous mode will be absent. So the presence or absence of this majority zero mode in this end state, is it doesn't really depend on whether the bulk symmetry is topological or not topological. So this is the example where this momentum space topology of this one-dimensional line meets with this. Well, it's the example how this real space topology appears in momentum space topology. So another example is probably more well known due to modern days of twisted bilayer graphene. So it was I think it was much earlier in high energy physics. So Tarangura and Cento they started this is two-dimensional Dirac electron and coupled with some kind of order parameter, some vector order parameter. And because of presence of this momentum space Dirac electron, if one integrate this Dirac electron, so the order parameter which coupled to this Dirac electron, the topological defect of this vector order parameter, which is the skyrmion, and skyrmion will acquire charge. In his context, in that context, this charge of this skyrmion was charge 2e. And later on, our friend Ugokmu, generalized this physics into quadratic band touching in 2 dimensions, where the electron has quadratic band touching. So the skyrmion now, in his case, in Ugok's case, was carrying charge 4e. When the skyrmion is condensed, in the early case of Tarangura and the Cento, they will generate charge 2e semiconductor. So in the context of Ugok, will generate the charge 4e semiconductor. So I think 2 years ago, last year, I think 2 years ago, maybe 2 years ago, Ashwin and Mark Zerter from Berkeley, they applied this understanding, the theory to interpret the semiconductivity in twisted bilayer graphene. So they propose interesting mechanism semiconductivity, which is due to the skyrmion condensation. The skyrmion carry electron charge. So this is a very beautiful idea where the topological defect carry a non-trivial quantum number due to the band structure topology of the itinerant electrons, right? So now I want to work on our case, which is our work is a twisted magnetic topology insulator. The title we use the twisted magnetic topology insulator, and this twist is acting on magnetism. It's not a mechanical twist. It's a twisting in the magnetic spin space. So this kind of twist, the meaning, the usage of this word twist in magnetism is actually older than twisted bilayer graphene, where the latter is a mechanical twist. Here is a twist in the spin space. So I should mention, so there are 2 accompanying works. One is from Liang Wu's group. The other is from Aaron Pomerkante's group. And Aaron Pomerkante's paper is much more theoretical than us. And if I'm interested on the more theoretical side, you can try to look at Aaron Pomerkante's paper. Yeah. So want to see. As I said, I should remember the audience. So I want to, study the interplay between conducting electron and the local moments, and put in interesting states of conducting electron with interesting states of magnetism, and see what's going on the right-hand side. The other interpretation is we studied the momentum space topology meeting with the real space topology, where the magnetic structure contains some real space topological structure, and see if we put the momentum space topology with this real space topology, what will happen on the right hand side. So there's 2 sort of understanding of the goal here, 2 sides of our goal. So yeah, so first we need to understand what are other magnetic states, other magnetic states beyond the simple ferromagnetism that was studied in Qi Kunshui's original experiment on quantized anomalous Hall effect, right? So for this purpose, we tried something very specific. Really, the specific treatment was trying to be, a little bit illustrative to motivate new experiment, new thoughts in this kind of direction. But but to motivate that, we perform a very specific calculation. So we for this our specific purpose, we just introduce chromium magnetic moment instead of a cobalt magnetic moment instead of chromium. Chromium sometimes behave a little bit more classical, so we introduce chromium. Cobalt. Cobalt seems to be a little bit more quantum than chromium. The reason, chromium is also used in this so-called 3D Kitab material, where one uses 3D transition metal ion to simulate the Kitab interaction. Yeah, because chromium can really become very quantum here. So we introduce cobalt magnetism. We dope the system, dope the bismuth selenium, which is a 3-dimensional topological insulator with cobalt magnetic ion. So we honestly perform this calculation by integrating out the conducting electrons and generate the effective interaction between these cobalt moments. And we assume the cobalt is periodic, which differ from the suggestion earlier. So we introduce the periodic area of cobalt atom, and from in this context, it's a triangle lattice. And we all call the interaction between the cobalt magnetic ion, and because of the presence of strong spin-orbit coupling of the Dirac electron, the effective interaction, effective superexchange interaction, or RKKY interaction between the cobalt magnetic moment is or has to be anisotropic. So it contain so-called Heisenberg interaction J, and also the so-called de-Orient schema real interaction D, antiferromagnetic and antisymmetric de-Orient schema real interaction. In addition, we have this so-called pseudo dipole interaction gamma. So it's a symmetric interaction, but if you write down the superchange matrices, it's a symmetric interaction but off diagonal. Yeah. So these are interaction between different components of the spin. And then we have this microscopic interaction between the local moment, and we couple it with external magnetic field. We use external magnetic field to tune the magnetic states of the cobalt at a cobalt magnetic system. So we write down the so-called we carry out the Ginzburg-Landau free energy analysis and obtain this phase diagram. So this is a generic phase diagram, which is expressed in terms of magnetic field and this dm vector. And the calculation for cobalt over the bismuth selenium is sitting along this line. So one can use a magnetic field to tune different magnetic states. So one can go from so-called magnetic spiral states, which is the non-collinear, non-coplanar spin configuration, and so-called skyrmion lattice, where the magnetic moment in a magnetic field form this kind of periodic area of topological defects, real space topological defects, and they form this kind of two-dimensional area of topological skyrmions. And when the field is large enough, the spin is being polarized by the external magnetic field, and the system form a ferromagnetic order. So we have three different magnetic states in this phase diagram. After understanding of the various magnetic states of the cobalt ion, so we want to see how does this feedback, how different magnetic states modify the momentum space topology or influence the itinerant conducting electron in this context. So to motivate that, let's consider a very old proposal by John Moore. So he was thinking about a surface of a three-dimensional topological insulator. When you introduce magnetism or magnetic order, so you break a time-of symmetry because of there is only one single Dirac electron or number of Dirac electron on the surface of one surface of the topological insulator. It will generate half, E square over H Hall conductance. So if you introduce magnetism, you get out the Dirac fermion, you get this quantum number Hall effect. And he was thinking about if the magnetic domain appears on the surface of Ti or on the surface of topological insulator, on this side the magnetization is up, on right hand side the magnetization is down. So there is a domain wall. So the mass of the Dirac electron have different on this the Chen number. Or the mass is different on the different side of this magnetic domain. So there has to be a chiral domain wall. Chiral, then it will be surface edge, so-called surface domain wall bound states on the surface of this topological insulator. So he was thinking about this kind of idea, and turns out the spiral states naturally generate or can be thought as a periodic area of this kind of domain walls. How do we visualize this? So this is the spin spiral state, and this is the spin modulation in the spin spiral state. And if you so this is the spin up, and gradually if you go along this line, the spin gradually goes to down. So and here is gradually goes to down. So if you go from here to here or go from here to here, you go, so the magnetization goes from pointing up and gradually to pointing down. This is more like a domain wall, between this upper region and the down region, which is very much like this example where the magnetization is up here and down here, and then is a chiral domain wall states, for the conduction electron. So that means for each of these modulation of this spin spiral state, there will be a gapless mode bounded to here. So each of these periodicity, each of these modulation will have a propagating chiral mode. Here the chiral mode is this direction. Here will be the other direction. So each spiral periodicity will hold counter-propagating domain walls. Yeah. So this is the feedback on the conduction electron for the spin spiral state. Yeah. So how about skyrmions? Skyrmion is a little bit harder to work with because it's a big object, and the spin configuration is a little bit more complex. To do that, let's look at one single skyrmion. Let's consider a single skyrmion. This is called a Nell skyrmion, where the spin configuration, when spin configuration goes from the center to the boundary, is gradually evolved from the center to boundary in this kind of fashion, without using the other transverse direction. They doing this from up gradually tilted to down. From North Pole to South Pole is from up to down, rather than it's like using rather using transverse direction. So this is called a Nell skyrmion. So for Nell skyrmion, you can sort of visualize this as a domain wall, in the radial direction. So in the central part of this skyrmion, the spin all pointing up, right? And in the boundary of this skyrmion, the spin all pointed down. So this is very much like this example. This is a domain wall from up to down in this x horizontal direction. Here it's in a radial direction. So this is like a domain wall. Domain wall is like a circular, and so that means there will be chiral edge states or chiral bound states, chiral mode bounded to this skyrmion. So each skyrmion, if you go from the center of the core of the skyrmion to the boundary of the skyrmion, there will be a gapless mode bounded here. So each skyrmion will have this bound state, a chiral bound state. Yeah. So the presence of skyrmion will necessarily twist the motion of conducting electron, and this is called a real space barrier curvature. So it's due to the scalar spin chirality. So the skyrmion, as it is, it carries non-trivial scalar spin chirality. So S cos S dot S is non-zero. So when you introduce conducting electron, which is Dirac electron here, there is a coupling between conducting electron with local moment, so when this electron moving around, adiabatically, it will acquire so-called real space, will experience the so-called real space barrier curvature from the background local moment spin texture, and this will generate the so-called Hall effect, and this is called the real space barrier curvature, and this will generate Hall effect, and this Hall effect was named by Nagosa Sen and Takura-san, called the topological Hall effect.
Okay.
Yeah, is a question? Yeah.
Yeah, I have a question. So this skyrmion is basically a magnetic domain in your case, right?
It's a real space topological texture. And
Right.
Yeah.
In your case, on the surface of this magnetized topological insulator, you're connecting magnetic domain and skyrmions. But the skyrmions do not have to exist by itself. I mean, they can bunch up and form like multiple skyrmion magnetic domain, right?
It can form a lattice. It's a lattice. Are you saying?
Can you? Yeah. In this picture, next one.
Next one. This one.
Yeah. So back. Yeah. So there are two domains in D, figure D, up and down.
Yeah.
Okay. So in each domain, maybe there can be many skyrmions together in the same direction, not opposite direction, same direction domain, skyrmions in each domain. So I'm asking whether skyrmion has to exist as size 1 skyrmion, or can that be like many skyrmions together?
You mean the topological number of this skyrmion?
Right.
It's not necessary to be 1, or it can be 2.
Right. Yeah. 2 or 3.
I think it's possible. But in our analysis, we don't consider the the number 2 or number 3. I think it's possible to have.
Maybe there's some misunderstanding. Let me think about it. Yeah. Thank you.
Kang, can I? Let me ask a question, sir. So, what is the total charge confined in a single skyrmion?
Say it again. What's
total electric charge confined within a single skyrmion?
Oh, we did not consider the electric charge here. We did not consider the electric charge, in this skyrmion. That's a good question. Yeah, one can ask the quantum number of the skyrmion carried here.
So so that's the one interesting question we discussed in the previous work actually.
I will check out it. I check out it.
So another question is, what happened in the case of vortex, not the skyrmion?
The vortex of
spin vortex. You consider the skyrmion type kind of defect, right? You can also imagine like vortex.
Vortex of what? The magnetic vortex?
Yeah, magnetic vortex. Yeah.
Magnetic vortex? No, we did not consider that. But this is also interesting.
Huh?
This is also interesting, but we did not consider magnetic vortex.
You didn't consider, but one thing I'm worrying is that this kind of topic is already discussed actually long ago. I think I also have a paper actually related to this issue actually. I just sent you actually by direct message actually.
I see. Thanks. I will check it out.
Nomura and also they also have a famous paper about this The charge confined in a text on the surface of a magnetic guy. Actually, you should look for the paper.
I should look at that. I should look at.
Yeah.
Yeah. So let me finish this part.
Huh?
Let me finish this part, and I was talking about here is so two different things happens here. So the Dirac electron itself carry, after being gapped or after coupled to the magnetism, it acquires this real space barrier curvature, but it itself carry, momentum space barrier curvature. The actual contribution to the transport will involve both. So it's a combination of real space barrier curvature and the momentum space barrier curvature in the actual contribution to the transport, whole transport. Let me just summarize. This is a very, it's a very simple piece of work. I think, people have thought about this earlier. So this, let me just summarize. This real space topology refer to real space spin texture in this context and generate a real space barrier for the itinerant electron. And the momentum space topology refer to the momentum space barrier equation physics. Broadly speaking, so the real space topology plus momentum space topology in this talk provide a rich topic and subject. So many things can be studied in this direction. There are further extension, when we consider the intrinsic topological order whose fractionalized exotic particle may develop some real space and momentum space topological features. So this is the first part, and I got 20 some minutes. Let me just sketch the second part, which is very different from the first one. So this is about fractionalization on the surface and the time rose symmetry anomaly in one specific quantum material, which is so-called 1T titanium disulfide. And this work is a collaboration with still the same people, grad student and postdoc, and a friend of mine, Jianpeng Lu from Shanghai Tech, and the experimentalist from Shanghai Tech, Shichao Yan. So let me, so this Landau's symmetry breaking theory has provided a modern foundation for our understanding of phase of matter, both classical and quantum phase of matter. And this is the phase diagram of liquid gas. And this is solid and gas and liquid. Apparently the solid has much lower symmetry than liquid and gas. And thus there has to be a phase transition if you go from solid to liquid and solid to gas. There is always phase boundary. You always meet a phase transition here and here. So, but the liquid and gas, they have the same symmetry. So in fact, the liquid and gas are in the same phase. You can adiabatically, you can gradually go from liquid and gas without crossing the phase boundary. So liquid and gas, from Landau symmetry point of view, liquid and gas are of the same phase. They are not distinct from symmetry point of view, right? So Landau's symmetry breaking theory has provided a modern foundation for our understanding of phases of matter until something exotic happened. So this is called the exotic phases beyond Landau's paradigm, Landau's symmetry breaking paradigm. And this is so in the 1982 there was discovery of fractional quantum Hall effect, and later there was proposal of quantum spin liquid, actually earlier in 1973, and revived. The interest of quantum spin liquid revived after the discovery of high temperature simultaneous activity. So this is this kind of phases, this kind of states cannot be understood in a classical paradigm of Landau. So all these plateaus, they have the same symmetry. They're characterized by different topological field theories. And quantum spin liquids, there are many different kinds of quantum spin liquids, and they can have the same symmetry, but rather distinct phase of matter for different kinds of quantum spin liquids. So there have been great efforts theoretically to understand or to classify these exotic gapless or gapped phases of matter, regardless of topological. gapless is not really, doesn't necessarily to be topological. Gapped and gapless exotic phases matter. And this is a slide, this is a paragraph I adapted from Xiaogang Wen's talk in 2012. So he listed some efforts at the time to classify these topological exotic phases of matter. He named it as a long-range entangled symmetric states, where symmetry is all the symmetry is preserved in these states, but the system carries so-called long-range quantum entanglement. And so all the attempt by himself in 2002, he tried to classify, using symmetry groups, act on the exotic quasi-particles. In the spin liquid context would be spin-ons, a projective symmetry group, so where the symmetry is realizing a projective fashion on the fractionalized spin-ons, and also these transcendental symmetry. There's 8 different symmetry enriched Z2 transcendental symmetry group, and Michael Hermle, he extended this to both spin-ons and the so-called visons or magnetic particles, visons, and he found that then there can be up to 1 million different symmetry classifications of Z2 topological order in 2 dimensions using group homologies. So in RAND, some using third group homology to classify different symmetry enriched topological orders. So there can be millions of these different phases, even though they have the same kind of symmetry, right, mathematically. So then the real question, or one of the important questions, how many of them can be actually be realized or cannot be realized, cannot be realized. Realized means at least to some sense, to another sense, is can one write down a model? It doesn't have to be physical looking, model to realize this kind of symmetric exotic state in principle, right? So it is understood now that some of these classified exotic states cannot be realized in strictly in 2-dimensional system, right? For those that can be realized in strictly 2-dimensional system, one may, in principle, construct the exact soluble model. May not be quite physical looking, but in principle, one could write these models to realize these very exotic phases. For those that cannot be realized in strictly 2-dimensional system, and they may be realized in an anomalous fashion on the surface of so-called SPD states, symmetry protected topological state, just like the topological insulator, where the time symmetry is realized in an anomalous fashion on the surface of the 3-dimensional topological insulator. So when the Lorentz symmetry is realized in an anomalous fashion on the surface of on the 2D surface of the 3D symmetry protected topological phases. So there was some efforts of this kind. So what are needed? So this kind of effort requires we first have a 3D SPD states, just like we have a 3D topological insulator where time symmetry is realized on the surface in an anomalous fashion, right? So with a single Dirac electron instead of even number of Dirac electron. So this require first we require 3-dimensional symmetry protected topological phase, whose anomalous surface that's realized the exotic state. Moreover, this also requires this exotic surface, the exotic surface state cannot be realized in strictly 2D. This the condition is a little bit too demanding. We first realize this exotic state on the surface of 3D SPD, but at the same time, and we require this state cannot be realized in strictly 2 dimensions. So this is a little bit too demanding. A less demanding possibility is we find the SPD state whose 2-dimensional surface state realize an exotic state in an anomalous fashion, regardless of whether this exotic state can or cannot be realized in strictly 2 dimensions. So this is a softer, more softer possibility. So we find a SPT whose 2D surface realize an exotic state in anomalous fashion, and regardless of whether this state can or cannot be realized in strictly 2D. So can this thing really happen in nature? So the natural material actually surprised us, then seem to be an example of this kind. And this is the proposal I'm going to make in the following. So this is a so-called transition metal dikryptonite, and this is 1T titanium disulfide. So this is a multi-layered three-dimensional system, and it turns out that this material has several interesting properties that surprise us, and it was regarded as a very stereotype of so-called charge density wave order in the 1970s, charge density wave materials in 1970s. The system developed a charge density wave, commensurate or incommensurate charge density at low temperature. Like the transition temperature is like 100, 150 Kelvin. So at a low temperature, the system developed a charge density wave. Whether it's a multi-layer or multi-layer, or monolayer. And this three-dimensional system also form this kind of spontaneous dimerization between the layers. This is a multi-layered system. It form this kind of dimerization automatically. Let me find a better figure for this. Doesn't seem to have a better figure. Yeah, anyway, so it is if you go from this z direction normal to this layered plane, it spontaneously form this kind of dimerization. Two neighboring layers they goes closer, and the distance between these dimerized layers is become the coupling between the dimerized layers is become weaker. So this is another view of this dimerization between the layers, and each of these is a layer, so they can form this dimer between the neighboring layer. Yeah, this is a dimer between the neighboring layer. So because of this dimerization between the layer, you can have different surface termination. So you can, in a three-dimensional system, then can be a finite surface, and the surface can terminate between this dimerization, between or cut inside the dimerization. So if it is between the dimerization, this is called the type 1 surface, where the type 1 surface terminate at one of this dimerization, one of this dimer. So type 2 surface is cutting in between one dimer, right? So these are two different surface termination. One can actually make an analog with so-called SSH model, Su-Schrieffer-Higgins model. So in this one-dimensional system, where the system often form this kind of dimerization, and if you terminate between the dimer, there will be no edge states. But if you terminate your surface, terminate your one-dimensional object in the dimer, there will be end states. This is so-called Su-Schrieffer-Higgins model, the result of Su-Schrieffer-Higgins model. And this is a three-dimensional, layered system. So you cannot directly apply Su-Schrieffer-Higgins model, but you can use this to guide your thinking. So we think, this type 2 surface termination, if we terminate between the layer, if you terminate inside the dimer, you will generate a surface states. So with this kind of thought, we can perform a calculation in the non-interacting limit. Consider a type 2 surface termination and perform a calculation and see whether there is a surface test or not. And in our calculation for type 1 surface, so if you terminate here, terminate at the end of the dimer, so there is no surface test at the Fermi level. But if you terminate your surface, inside the dimer, there will be a surface test. So this is the calculation in the non-interacting limit. So without including any kind of interaction, if you consider a three-dimensional system of this kind, if your terminal system in this fashion right here, a terminal system right here, that will have one of them will have surface state, the other do not, right? In the non-interacting limit. So what about if we introduce interaction? If we introduce interaction to the system, right? If we introduce interaction to the system, so we have known that the system develops charge density wave, and the charge density wave is developing in such a fashion that 13 of these titanium atoms form a cluster, from a David star cluster of this kind, right? 13 of these titanium atom, they form this David star cluster, and these clusters themselves are organized into a super triangle lattice. Themselves organized into a super triangle lattice, right? So this is called the so-called the cluster, David star cluster. And if you count the number of electrons or number of atoms, there are 13 electrons in this David star. 13 is odd number. So that means there is always unpaired electron being localized in this cluster. So the electron is localized in cluster fashion, on this triangle, on this David star cluster. And this localized cluster, localized electron, and in this limit form a motor insulator, form a local moment in this low temperature, and give rise to a local spin 1/2 local moment at this super site, at this cluster site. And this cluster themselves are forming a super triangle lattice, And so the result is there is a spin 1/2 local moment here, right? And this spin 1/2 local moment is forming on the surface, on the type 2 surface, of this three-dimensional bulk system. So, and because of this spin 1/2 local moment here, time reversal symmetry is realized in an anomalous fashion. So we have t squared equal to -1. So this is a Kramers doublet at each of these David star cluster. In contrast to the bulk, where each of these unit cell carry time reversal, t squared equal to +1, right? So the time reversal symmetry is realized in an anomalous fashion on the surface, on the type 2 surface here, right? So whether there is a local moment or not, one can look at experiment, use the experiment to guide the thinking. And this is the experiment performed by Shichao Yan from Shanghai Tech. He introduced use lead doping into this type 2 surface, where he introduced conducting electron into the system. So he observed a sharp Kondo resonance on the type 2 surface. As you cool the system, there is the peak becomes sharper and sharper. And this is a Kondo resonance peak in his STM measurement. And this is a field dependence, and up to 8 Tesla, this peak still preserves. It means the interaction is strong. So the presence of this Kondo, this the Kondo resonance in STM scan for different doping percentage. So there is always this Kondo resonance. The presence of Kondo resonance on the type 2 surface means there exists a local moment of formation. There has to be this local moment, emerge on the surface. So there is a surface state, and the surface state form a local moment. And time reversal symmetry is realized in an anomalous fashion on the surface of. If the time reversal symmetry is not realized in an anomalous fashion, there is no local moment, and there is the local moment here. So we want to understand the fate of this surface state in the strong correlation limit. Apparently, the system is strong correlation. They form the local moment, and what is the fate of these local moments in the ground state? And so the proposal is the local moment form a spin liquid. Why is that? So remember, each of these David star trap a spin 1/2 here. And these David stars themselves are organized into a super triangle lattice. So this is the perfect example of spin 1/2 triangle lattice magnet, right? Except it's on the surface. It's on the surface. It's an interacting spin 1/2 local moment. Apparently, charge fluctuation is shown. So it's not a simple Heisenberg limit where the system forms so-called 120-degree state. Here it's not. And because of strong charge fluctuation, the system actually form a spin liquid. It's a triangle that is spin 1/2 Hubbard model. Triangle where that is spin 1/2 magnet. Right. So I only work with Patrick Lee and Wicklow and his student and postdocs. So we perform this kind of microscopic calculation. The model, the effect model for this interaction spin 1/2, and this is for model layer. This is really this is not for surface spin liquid. This is a knowledge developed for model layer 1T tellurium disulfide, where the model is some kind of XZ version of the ring exchange. Because the ring exchange, the system can form this so-called spin-on-forming surface spin liquid. So this is the only understanding for model layer. And this surface model layer, surface layer of type 2 surface of 1T disulfide is not very far from this model layer. One can use this result here, use this understanding and apply to the surface spin liquid for the type 2 surface. So is there any experimental evidence for this presence of spin-on-forming surface? It turns out there is a natural physics work by Mike Cromie. It's an STM measurement. It's not on monolayer 1T. It's not on monolayer 1T titanium disulfide. It's on monolayer 1T titanium diselenide, where they do see this kind of some kind of super modulation. There is some kind of finite momentum modulation, and they propose on the Patrick's guidance. They propose it's due to this 2kF process of spin-on-forming surface. It's related to this spin-on-forming surface 2kF instability, where there is a spin-on-forming surface, but the spin-on-forming surface has this 2kF kind of instability, and it's generate this kind of peaks in the STM spectrum. So want to extend this understanding to our type 2 surface, where the surface terminates at a type 2 in a type 2 fashion, and there is local moment on the surface. We want to detect if there is a spin-on-forming surface in this model layer. So because of the time, how much time do I have?
You can use around 10 more minutes.
10 minutes is fine. Yeah, 10 minutes you be good. So as I said, the 3D surface, is quite different from model layer because the time symmetry is realized in an anomalous fashion. So the local moment is otherwise appears because of the combination of this anomalous time symmetry and the strong correlation. Yeah. So
yeah. You mentioned the anomalous time symmetry a couple of times. What does it mean?
Yeah. So here, let's see. Yeah. So this is the type 2 termination. This is type 1 termination, right? Right. So this is the bulk sample. The bulk, the unit cell contain even number of electrons. 2 sides or 4 sides depends on how you use your unit cell. Well, it's 4 sides. So the time symmetry T squared equal to +1 for this system, right? Right? Because unit cell contain even number of electrons.
I see.
But if you terminate your surface, if your surface is terminate here, so then is a dangling site, unpaired site, which carry a cluster. Really, it's a cluster contain all number of electrons in this inside. Time symmetry is -1 because this is spin 1/2 or carry one electron, even number all the number of electrons. So time velocity equal to -1, right?
Okay, I understand.
Yeah.
Sorry, so another question. You showed the spin Hamiltonian relevant to the surface of this system, right?
I show set that again.
You show some spin Hamiltonian that describe the surface of the system.
Yeah. So yeah, here.
I mean, how is it related to this system? The Hamiltonian is very complicated. You have many interaction term, right?
Oh yeah.
But are they allowed in this system, or you have a force interaction and also? Yeah, I don't know how. Yeah.
So this is really, as I said, I know here is XSZ version of the ring exchange model. So if you set gamma to 0, that's become the standard Heisenberg and the ring exchange. This is the ring exchange. This is the ring exchange. As long as gamma is not very large or very small, or very negative when small, very large, very positive when very large, the system can realize the first time is not very far, very different from the case where gamma equal to 0. Right? So you have this ring, you have this spinor Fermi surface. The reason this ring exchange appears is because of strong charge fluctuation in the weak model regime. So the charge gap in the system is not very high. You know, the electron is not strongly localized, but not very strongly localized. It's a quasi-itinerant electron. Quasi-itinerant, it's strongly charge fluctuating. And then you do perturbation theory, you need to go to high order. Right? So high order means fourth order. If you go to fourth order, you will have this ring exchange, right? If you go to second order, you have Heisenberg. If you go to high order, you get a ring exchange. Yeah.
Okay. Thank you.
Yeah. So yeah. So then imagine if the surface, this surface, as let me remind you again. So this type T surface, each of this cluster has a spin 1/2, and time symmetry is realized in an anomalous fashion. And this is spin 1/2 cluster. They organize into a triangle lattice. If I use the result of this monolayer, if I use the knowledge, Patrick Lee's and all the knowledge on this monolayer, so the spin 1/2 actually become a spin-on Fermi surface. Now the question is, how does one detect the surface, this surface spin liquid or surface fractionalization? How do we actually experimentally probe this surface state? So one has to rely on some surface probe, right? Very surface probe, either transport or spectroscopic surface probe. So this comes to the proposal here. So surface is an angle resolved photon emission type of measurement, and this is the early work by Mackenzie and Professor King in 2020 on PD chromite. So this is also a layered material where the PD form a connecting electron, and chromium is a local moment. So this connecting electron, this is local moment. So if the system is in paramagnetic phase, the local moment is disordered, it doesn't really order. If you do angle reserved photon emission, what you see is the surface Dirac surface Fermi surface of this PD itinerant electron. This is the Fermi surface, and you see this kind of energy momentum dispersion, which is this kind of quasi-particle peak here and here and here. These are equivalent and in a paramagnetic state. But if you lower the system and the chromium in the 3+, you carry magnetic moment, it will develop a magnetic order. The magnetic moment coupled with the connect electron on the surface. So it will generate a replica peak because the system develops magnetic order, and the magnetic order is at finite wave vector, order at finite wave vector, finite momentum, finite wave vector. It will create a replica peak for the connect electron, for the surface connect electron. So in the angle reserved photon emission, you will observe a replica peak, a replica band. Originally, the dispersion is the electron dispersion is here. Now, because of the chromium develop magnetism, develop magnetic order, you will create a replica band. This replica band, it shifts this to here, this replica band, and shift this to here, then it's a replica band. Right.
So is the magnetic order SDW or antiferromagnetic order?
So here, although the surface, Fermi surface seems to be nesting, this PT
Yeah.
nesting, and
so that's a magnetic zone, a Brillouin zone boundary, right?
Yeah, in some context, because there are series of compounds, in some material they do observe this CW due to the quasi-nesting of the Fermi surface. But in this particular context, the magnetism is from the chromium local moment. From the chromium local moment. Yeah. So the chromium local moment has magnetism and orders at antiferromagnetic order at the finite wave vector and create a
antiferromagnetic order. Okay.
Yeah, create this finite momentum replica spectrum.
Yeah. Thank you.
So guided with this idea, one can ask if one have surface, conducting electron. If one have a surface conducting electron on this surface, can one probe the underlying magnetism, underlying surface spin liquid here, right? So this is the calculation we perform here, and without this is a convolution between the conducting electron spectral function and the spin correlation function. This is a convolution. So if it is magnetic ordered, this is a delta function peak at a zero frequency and finite wave vector will immediately create a replica band shifted by a wave vector Q. This is what happens in this context. Originally had this spectral weight, now had this replica dispersion here due to the finite wave vector ordering of the magnetic moment, right? This is a replica of this one. This is a replica of this one, right? So yeah, and this is all replica of, yeah. So in this context, in our context, the spin structure factor is not a delta function peak. It's not diverging at the ordering wave vector Q. It's a spin on continuum contributed spin correlation. It has this 2kF type of structure at the zero wave vector, zero momenta, etc. And this is the dispersion of the free quasi-particle of the conduction electron. Now convoluted with this spin structure factor, and this is the original principal peak, and convoluted with this SQ, will generate replica peak of here and generate replica peak of this here, and shifted by this the dominant peak of this spin correlation function. So this will give you a convoluted contribution from the conducting electron and the surface spin liquid spin correlation. So this is the proposal to probe surface spin liquid correlation. So let me just summarize because I'm running out of time. So the following this only very abstract proposal, only abstract idea to realize spin liquid in an anomalous fashion, regardless of whether this surface exotic spin liquid can or cannot be realized in strictly two dimension. As long as it can be realized it is realized in an anomalous fashion on a three-dimensional surface of a symmetry protected topological phase, so-called SPT state. And regardless of whether it can be or cannot be realized in strictly 2D. So this is still already very interesting. So type 2 surface of this 1T disulfide titanium disulfide seems to be a rather unique system to host a surface spin liquid in an anomalous fashion on a three-dimensional SPT state. And it seems to pose some very theoretical and experimental challenges so far. And let me stop here and take some questions. Yeah, thanks very much for staying to the end.
Yeah, thank you very much for very nice talk. Yeah, now talk is open for question or comment.
And so I have one question actually.
Mm-hmm.
So actually, I don't understand why do you assume the spin liquid in the second part actually. What is observed in RPS is because you see some kind of modulation in the energy electronic spectrum, right?
Mm-hmm.
But why do you assume the spin-forming surface?
Why do I assume the spin-forming surface?
I mean, based on the measured data, what we can say is that there's some kind of modulation in the surface energy spectrum, right?
Mm-hmm.
Why is it necessary to assume the spin liquidity with the spin-forming surface?
Oh, you mean this measurement? You mean this measurement? This is the actual measurement.
Yeah.
Yeah. So yeah, this is Patrick Lee's theory. Yeah, they're collaborating on this. Patrick Lee is providing the theoretical interpretation here. So first there is a calculation. There is this calculation. That so this observation here, so they do not directly see this the Fermi surface or 2kF. What they see is because this is not a spin resolved STM, this is really seeing some kind of charge modulation. And this is STM, but it's not a spin resolved STM. This is the electron density. So what they see is they see this peak, this peak Q. And this is 6 different Q because of this, really because of symmetry. These are Q1, Q2, and all these blue Qs are equivalent. So they think this is related to this 2kF, and this P1 2kF peaks, and it's a linear combination of these 2kF peaks as they draw here. This P1 and P2, linear combination of this P1 P2 generated this Q, and because of that they propose, and this is at the income measure vector. They propose this is due to the instabilities of the spin-forming surface. Yeah, and this is the supermodulation on the background, the CDW, because the system already formed this kind of cluster CDW, and this peak is not at this CDW peak. It's at a new peak. It's an income measure peak. It's due to this local moment interacting with each other. Yeah.
Anyway, so this spin-forming surface is one way to explain this kind of incommensurate peak observed in experiment, right?
Yes.
Am I right?
It is one way. Yeah.
Yeah. You also mentioned that if you perform the spin reserved RPS, is it possible to measure the spin-forming surface?
It is possible. If you do spin resolved RPS, you will delay. You will see some spin texture. You will see spin quantum number.
Yeah, but I don't know. Maybe the Professor Chang give no better, no more actually.
Yeah, I was gonna comment it as an experimentalist because this Davis star is big, so unicell is very large. That means all the features will be seen within very small momentum range. So experimentally, it will be very, very challenging, unfortunately. But this is an interesting idea. Another thing about RPS is that you cleave sample, then we get both type 1 and type 2 surfaces. So we get mixed signature from two areas. So that's another problem.
I think related to this, as far as I know, I think that even for spin resolved RPS, basically the coupling between the photon and electron. Anyway, we need to charge an electron to see some signal from RPS measurement, even for spin resolved RPS. So the coupling constant is charge, not spin. That's what I understand. Am I right? I mean,
are you asking me or?
To both you and Kang Chen actually, because according to Kang's idea, basically, if you perform the spin resolved RPS, we can basically prove the spin-on-forming circuit. Basically, spin-on is chargeless. There's no charge of the spin-on, but just carry some spin degree of freedom.
Right.
Yes.
If you assume some particle which has only spin equal freedom, is it possible to prove it by using the RPS? Spin equal RPS?
Not directly. That's the same
Yeah.
thing as the spin charge separation. We probe electron, but electron
Yeah.
decays into spinor and holons. So
Exactly. Yes.
in 1D.
Yes.
So yeah, it has to go through one more step.
Yeah. I see. That's why I'm a bit confused actually. Is it really possible to measure the spin of forming circle using RPS?
Yeah, theory has to come in. Yeah.
Okay.
I see. Maybe with low photon energy, we look at very small momentum range. Maybe that's possible with the laser RPS. So I need to think about it. But anyway, it's an interesting proposal.
Okay.
Yeah, Gang, can I ask you about the spin liquid phase of this that occurs here? I mean, so you were emphasizing that this is spin liquid phase you obtain from a protected surface state. So, I mean, does this have some kind of an anomaly that would not be possible in purely two-dimensional system?
You're asking this. I'm saying this kind of let me go to the introduction part. So if I understand your question correctly, so you basically try to ask this kind of the surface state I'm proposing here. Although it's realized in an anomalous fashion on the surface of a 3D SPT on this in this context, this state can in principle be realized in 2D, right?
Yeah.
So so
I mean, for instance, like in topological insulator, you cannot have single Dirac cone in purely two-dimensional system, but that's possible in topological insulator surface. I mean, so I'm just asking you, like, about the spin liquid state. Is this to be understood as something analogous to that?
Oh yeah, so yeah, that's a good point. No, so this surface state, this surface spin liquid state proposed here could be realized in strictly 2D, right? It could be realized because in monolayer system, it's a strictly two-dimensional system. One could realize a spinor-forming surface state in principle, right? This differs from these earlier requirement where this two-dimensional surface state cannot be realized in a strictly two-dimensional system, right? So the only requirement has two. There are two requirements. First, this state is realized in a surface of a 3D SPT, but at the same time, this state that being realized on surface cannot be realized in 2D. In the proposal, in my proposal here, so in our proposal here, this condition is being softened because we realize this state in the surface, but on the other hand, we do not require this state cannot be realized in 2D. It can be realized in 2D. But in this particular context, it can be realized in 2D. Also, it is realized in an anomalous fashion in 3D. This is still very, very uncommon, right?
Okay, thank you.
Yeah.
Okay, is there any other question or comment?
Can I give one question? Can you hear me?
Yes.
Okay, very nice talk. I have a question about your 2D surface state and the 1T tantalum disulfide. The configuration you show here is as far as I know, if the stacking order like this, then the underneath top surface, it becomes band insulator. But you claim that the localized spin is screened by the itinerant electron. But as far as I know, the yellow configuration you highlighted here, it becomes band insulator. But how can you explain the condo screening?
In the left-hand side. Yeah, so the condo screening appears when you introduce lead doping. When you introduce lead, there is a doping here.
Yeah.
There is a doping. You introduce itinerant electron by doping. Yeah.
Okay, then the lead doping leads to the stacking port. So your system does not have the stacking order that you showed in the previous slide, right?
The stacking.
Yeah.
Yes.
If the lead dopant leads to the stacking port, so your system has the metallic stacking order underneath the surface, then I can agree your point. The localized spin on the surface is screened by the itinerant electron. But the schematic drawing showed that you showed here, it doesn't have any itinerant electron underneath of the surface, since the yellow stacking order leads to the band insulator. So, but
I think let me see if you understand. I understand you correct. Here in this slide, we are not talking about any kind of doping. This is the in the perfect limit where you have type 1 termination and type 2 termination. There are distinction between type 1 and type 2, and this has already been, I think, noticed in a work by these people, but they not really emphasize this time also anomaly. I don't think. Yeah. Anyway, so there is a distinction between type 1 and type 2, and we are saying this type 2 this form this local moment, and this is whether this local moment is formed. This can be evidenced in this Kondo resonance if one dope into this introduce lead doping, which introduces a metallic island into the system, and the metallic side metallic moment, metallic degrees of freedom coupled with the local moment and form this Kondo resonance. If there is no local moment, you will not be able to understand this Kondo resonance, or there is nothing to form this Kondo if there is no local moment. On the other hand, there is all the work, I think, on this 1T tandem disulfide by MuSR people. They confirm the presence of this local moment formation inside this David star. It's MuSR and NMR work it's also Nature Physics paper in 2017, I think. Yeah.
I agree that point, but I have some concern.
You have some concern, yeah.
Whether the itinerant electron comes from. Since your system has some band insulator underneath of your localized spin in the David star, but you claim that the lead dopant provides some itinerant electron to screen the local spin moment.
Yeah.
But I don't actually I don't agree with that point, because the lead dopant can lead to the many domain wall structure in the Charles density wave system that can easily lead to the stacking port. So the bottom line is that your system does not have the stacking order, the like figure D that you showed in this slide. So that is my point. Yeah. Okay. Yeah. Thank you for your answer. Yeah. Very nice talk. Yeah.
Okay, then is there any other question or comment? Yeah, then let's close state seminar. Yeah, let's give big hand to state seminar.
Thank you.
Yeah, thank you very much. Yeah, very nice talk.
Thank you very much.
Very nice talk.
Yeah. Okay, I'll check out your paper. Yeah.
Yeah. Thanks.
Okay, thank you.
Yeah.
Okay. Bye.
Oh, bye.
Yeah.